Okay, let's get started. Good morning and welcome back. So I got the calendar pulled up here just to look ahead what's going to happen. We got one last week of regular lessons. We have 3 lessons to cover. We'll finish up 5.3 today and 5.4. Those are pretty short actually. And then for the remainder of this week, Wednesday and Friday, we'll cover 5.5. That's a much heftier section and takes longer to go over. And the entire next week we'll spend on doing final review. Okay? Okay, so if you look at those 2 screens, you see that line there. It took me forever to figure out what's going on with that line. If you're watching this on Boilercast, you won't see it. So if you look up, there are 2 balloons on the ceiling, and the strings are what's casting the shadows on the screens. So it took me forever. I was wiping this thing, trying to figure out what's going to happen. Anyway, somehow they ended up there, and we'll just try to work around those strings, okay? Okay, so we're going to look at 5.3. Finish that up first. All right, so first I want to do just a very quick review of what happened last Friday when we did this section, in case you're rusty on that. So quick review from last time. We saw 2 versions of the fundamental theorem of calculus. Fundamental theorem of calculus version 1, it established the relationship between differentiation and integration. Okay? The derivative of the definite integral of the function f of t, starting at t equal to 0, ending at t is equal to x, ends up being equal to the function itself. Quick example. The derivative of the integration from t equal to 0 to t is equal to x of the function sine squared of 4t squared plus 3, it really doesn't matter how complicated that function is. If you think in terms of the area, it doesn't matter how complicated it is. We're looking for the area underneath that and looking for the rate of change of that. According to fundamental theorem of calculus 1, this is simply equal to the function itself with a t being changed to an x. And the reason behind this being a t and that's an x is because we cannot reuse the same variable here and the integration limit. They have to be different. So that t is just a bookkeeping kind of variable. There's nothing really special about it. Okay, so that's the first version of the fundamental theorem of calculus. And also remember, we sometimes have to use chain rule. It happens when the integration limits, specifically the variable one, is not just an x. Okay, so if we're integrating from 3 to, say, e to the 2x of this function, again, think in terms of the area. We're looking for the area underneath this function, between this function and the x-axis, from t is equal to 3 up to t is equal to e to the 2x. That's going to be some number, but it just doesn't look like a very simple thing. Now remember, with the chain rule, we call that complicated limit a u. So this thing really is y in terms of a function, new variable u. Then, by the chain rule, to find the derivative with respect to x, we take the derivative with respect to the intermediate variable u, which is e to the 2x, then multiply by the derivative of that u, the standard chain rule stuff. The first part here is simply FTC1 again, with u in place of x. Okay, so dy du with y being this thing will simply give us u cubed 1 plus u squared. And then du dx, derivative of that, e to the 2x times 2. Okay, finally we clean this up. 2e to the 2x, let me put it up here. You want to get rid of u. And we get that. All right, so there's the first version of the fundamental theorem of calculus. It ties together differentiation and integration, and then complexities involving using chain rule. Notice that the lower limit, 0, 3, it really doesn't matter. As long as it's a constant, it doesn't come into play at all, right? This number down here has no bearing whatsoever in the derivative. That number tells you where the accumulation of the area starts. And if you're looking for the rate of change of the accumulation, it really doesn't matter where you start. It's simply somewhere you have accumulated up to this point. Okay, so now the second version of that, FTC, fundamental theorem of calculus. It gives us a very convenient way to calculate the area between the function and the curve exactly. The definite integration from a to b of the function f of x dx is, let me finish writing this, capital F, where capital F is the antiderivative of lowercase f at b minus capital F at a. As long as you could find capital F, you simply find out what the difference between that function at the right endpoint and the left endpoint of the accumulation of the area. I think last time we did one example like this one. And this is asking, what is the area between the function sine of x, starting at 0, ending at pi over 2? What is the area between that and the x-axis? Okay, so you have a sine that starts at 0, goes up to 1 at pi over 2, comes back down, and so on. FTC2 says, find a function whose derivative is sine of x. And we know that's negative cosine. Then, remember, one way to write out what happens next is that straight line with the integration limits staying in the same place. And what this means is first we plug in pi over 2 in for x. Then we subtract away what happens when we plug in 0. All right, so that function right here with x being pi over 2, and then the same function with x being 0, take the difference. Be careful, you work with this first, and then that, right? And here we get 0 minus 1, we get a 1. So that area is exactly 1. In some applications, FTC2 is sometimes called the net change theorem. And the reason is pretty clear. You can see the only thing that matters in the end is the net change of the capital F function between the right and the left end. Whatever happens in between, with some restrictions that we'll talk about in a little bit, whatever happens in between is completely irrelevant. It's what happens to that function at the right end and that function at the left end. For example, in physics, if f of x is force, then the integration of force gives you work. So this gives you the work done by that force starting at x is equal to a to x is equal to b. Now if you think about force being gravity, for example, this is telling you that all that matters is where you start and where you end. So when you're lifting something against gravity, all that matters is the net change between the initial and the final height. It doesn't matter how you get there. The amount of work done by gravity or that you have to do against gravity is the same. If force behaves like that, the force is called conservative force. But that's you'll get more into that in physics. Okay, so sometimes you'll see net change theorem, and all that's talking about is just FTC2. Here's another example that we did last time. Remember, there was one special exception to the power rule when x is equal to -1. And that special rule gives you natural log of the absolute value of x. Be very careful with the absolute value. We have to make sure this function is always defined. So here we get natural log of 2 minus natural log of 1. And of course, natural log of 1 is 0, so we get natural log of 2. We have many different ways to define E that you've seen so far. We also have many different ways to define the natural log. So what happens here is actually one way to define the function natural log of x. If you look up here, the 1 here doesn't matter. We end up getting a natural log of 1 that's at 0. The upper limit ends up being natural log of that number. So extrapolating that, the integration from 1 to a of 1 over x dx gives us natural log of a. So this is one of the first ways in the history of mathematics that natural log was defined. In fact, it was specifically in one of the earlier ways defined as the area underneath the function 1 over x from x is equal to 1 to x is equal to a. Okay? It's one of the oldest ways that natural log was defined. Okay? So again, like I said, there are many different ways to define natural log, just like there are many different ways to define the function e. Okay, now very important thing here. With the net change theorem earlier, I said that as long as the function satisfies some restrictions, then it doesn't matter what happens between the beginning and the end. That important restriction, let me write down this again. This function, this fact here is true, very important restriction, only if the function lowercase f of x is continuous. If it's not continuous, then this is no longer true. So in terms of physics, if you imagine the work being discontinuous, which we don't normally encounter, then the force being discontinuous in the work is going to be a little bit more careful with the way how we calculate work. Let me give you one example where the function is not continuous. And you can see it ends up being quite a mess. Let's find the area under f of x is equal to 1 over x squared. From x is equal to minus 1 to x is equal to 2. Let's make a sketch. 1 over x squared looks a lot like 1 over x, except it's always positive. So we're looking for the area from minus 1 to positive 2. Now with this picture in front of you, obviously right away, you can notice a problem when we ask for the area. This thing shoots up to infinity. If you keep accumulating the area underneath it, there's really no bound to it. It just keeps going up and up and up. So it is clearly the function that we're integrating is clearly not continuous at x is equal to 0. So this thing here, integration from minus 1 to 2 of 1 over x squared dx, cannot be found directly from FTC2. It violates the very important restriction where the function must be continuous. This is one of those integrals called an improper integral. And next semester, when you take 162, we'll spend quite a bit of time on improper integrals. There are many different types, but one common theme is one of something to do with discontinuity or something going to infinity. That's when improper integrals happen. Okay? Now let's see what happens. Let's see what happens if we use FTC2 incorrectly anyway. Let's see what happens. Let's just see what happens. See what we get. Okay, if I didn't have this picture in front of you and I didn't notice this function being discontinuous at some point between here and here, and I blindly use it, then remember, add 1 to the power, dividing by the new power, and then evaluate at the end points. Be very careful with the sign here. First, we're plugging a 2 for x. Subtracting away, now we're plugging a -1 for that 1. Okay, this is a very common thing with FTC2. If you have negative signs in the limits and the function itself, you have to be very, very careful with the second part. You got minus signs all over the place. If you're not careful, this can be easily screwed up. So watch out for those signs. It's the function evaluated at 2 minus the same function evaluated at -1. So we get -1 minus, this is a plus, so minus another 1. That's -3/2. Now this clearly cannot be right because the entire region is above the x-axis, right? Remember, that means the area has to be positive. And if I used FTC2 incorrectly, I get something that's obviously wrong. It's a negative number. It cannot be right. There's no chance for it to be right. Okay, how we handle that, that's for 162. There are lots of different ways to handle that. We have to use something to do with limits, actually. But anyway, in 162, you'll figure out exactly how we can handle this kind of situation. For now, we'll just leave that area as a mystery. Okay, so that wraps up 5.3. Now let's talk about 5.4. There, much better. Now 5.4 is pretty short. We can probably finish up pretty quickly. My plan is if we have time left today, I'll talk about grades. Is that okay? All right. Okay, in 5.4, we talk about indefinite integrals. The integration of f of x from a to b is a definite integral. And you can think of it as being the integration limits being specified. You definitely know where you start and definitely know where you end. So the important distinction here is that the integration limits are specified. If I just write the integration simple without the integration limits attached, then we call that an indefinite integral. FTC2 tells us that the definite integral is simply the antiderivative of the function at b minus the antiderivative at the function at a. When you take away the integration limits, you're still dealing with the antiderivative. And what you end up getting is simply the function capital F plus the usual constant of integration, c. So you want to think of indefinite integral as just a shorthand notation for finding the antiderivative of certain function. The important distinction here, the definite integral will always give you a number. You're looking for an area. The area is 3, 1, 5 pi, whatever. The indefinite integral will give you a function of x plus some constant of integration c. Okay, so all it really is just a shorthand for finding the antiderivative. Shorthand notation for finding the most general. That's why we have to attach that plus c. We want it to be perfectly general. Okay, and there's nothing more to it. It's just simply finding the antiderivative of a certain function. Couple of quick examples. All right, so we got this thing here, 4x cubed minus 5 radical x over x. It's an indefinite integral. We expect a function of x and a plus c at the end. This can still be interpreted as some kind of area, but now we don't know where we start, and we don't know where we end. So that plus c is important. The plus c, think of the plus c as a way of telling you what has happened up to a certain point that you're looking at. Okay, remember how we do this. We've got to write everything back, put everything back in terms of x to the n. I only have one thing in the denominator, so I can divide everything on the top by that same thing downstairs. So here I'm going to get 4 times x to the third over x to the 1/2. The net difference is x to the 2.5, or 5 over 2. This one here, the 2 radical x's go away, so we just get a 5. Okay, now we apply the power rule. We add 1 to the existing power divided by the new power. Don't forget that 4 that was sitting in front of it doesn't participate. And this 5 carried an x to the power of 0. So that 5 doesn't do anything. Now we add 1 to the existing power, which is 0. It's now a 1. Dividing by the new power, that's a 1. So a constant, remember, just gains a variable when you integrate it. Want to be perfectly general, so we add a plus c. And now what do we get? We get 4 times the reciprocal of that. That's 8 over 7. X to the 7 over 2 minus 5x plus c. Okay? Now if later on you decided, now I want to know the area underneath from 1 to 2, for example, then I simply take this function, I plug in 2, subtract away what happens when this function, with this function when I plug in a 1. You do exactly the same thing as FTC2, working with that function. That c ended up being irrelevant once we turn this back into a definite integral. All right, one more quick example. All right, so let's see. The first two seem pretty easy. We add 1 to the existing power, so it becomes a 3 divided by the new power, so 5 over 3. This one's just like the 5 before, gains a variable. All right, so then we have 8 times the indefinite integral of 1 over 1 minus x squared. Anyone remember what function has a derivative of 1 over radical 1 minus x squared? Inverse sine. Good, good. Sine. Right. What would the inverse cosine look like? Minus. Okay. What about inverse tangent? Good, good. He's very excited about inverse functions. Good, good. Okay, so this is inverse sine. And then we add a plus c, right? Okay, so don't just use the power rule all over the place. There are exceptions like 1 over x, and then there are other kinds of things that power rule doesn't work for you. Okay? All right, so that's 5.4. Like I said, there's really nothing to it once you understand the definite integration. Then indefinite integration is pretty straightforward. Nothing more than a shorthand of finding the antiderivative. All right, now let's talk about the grades. So I put together this little presentation here. Okay, that's what we'll be talking about. All right, so first of all, the basics. Remember, the maximum points you can earn this semester is 708 points. Your homework accounts for 100 points altogether. Your quizzes altogether account for 100. Each of the 3 exams is 100, and then there's a 200-point final exam. So that means that from this, you still have 200 points to come, which accounts for roughly a third of your grade. So roughly a third of your grade still hasn't been determined. So everything you have up to this point can still change depending on how you have been doing these 5 things. Now, to figure out what you got on homework and quizzes, go into WebAssign, look at My Grades, and click on Raw Scores. So this is an actual student's gradebook. Of course, the name is removed, but it's an actual, someone actually did this work. So to look at your homework score, look at the homework. Don't pay attention to the max possible or your score. You want to pay attention to the percentage. So this student here has got 99.43. So that means he or she has 99 points. Okay? Quiz is the same thing. Don't look at the max and the score. Look at the percentage. This student has 92.25, 92 points. And the 3 exams, the students got 100 on the first one, 84 the second one, and then 92 on the last one. There's also a row for bonus right here. That is not complete. There should be an 8 when it's all said and done. You had 2 calculus concept inventory quizzes. You took one earlier this semester. There'll be another one this week. And then you had 2 surveys they wanted you to fill out. So each one is 2 points. Altogether is 8. So the max you can get is 8 on the bonus. The bonus just adds on top of whatever you got. So this student so far with bonus not accounted for yet has 99, 92, 100, 84, 92. So pretty good score. Okay, does that make sense how you find your grade? Scores? Okay. Now, the way we determine grade is a little bit, is most likely unfamiliar to almost every one of you. So let me try to run down how we do this thing. Here is a hypothetical recitation with 11 students. So here are the scores of everybody. Homework, quiz, exams 1, 2, 3, final exam. So this is the kind of thing that we'll be looking at after the final exam. Each recitation has one thing, a set of data kind of like. Of course, in a real recitation, we're expecting, we should have 30 to 40 students. Here I have a smaller section, not a big deal. So we rank them by the total here. Okay? We'll come back to this in a little bit. The first thing we do is we temporarily ignore the homework and quizzes. The reason is because each TA writes his or her own quizzes. So, and you know, we have no control over how they write and how they grade. Certain TAs may write easier quizzes. Certain TAs may grade easier than others. So we try to normalize that by momentarily ignoring the quizzes and the homework. The only thing we look in the first step are the exams, because everybody took the same exams, right? So the first step is we just look at the exams. Somebody in the math department is going to decide out of the 500 points from the exams what an A, B, C, D, and so on will be. As an example here, let's use these hypothetical numbers. So suppose that at the end of the semester, we've determined that an A, just the exams alone for the moment again, an A is 436, an A minus is 420, B plus is 404, and so on. So here are the hypothetical numbers we looked. Now that same hypothetical recitation we just looked at, with the homework and quizzes removed, here are the rankings. We look at how many students that's got 436 or higher. 1, 2, 3. So that means 3 A's. We look at how many students have 420, higher or equal to 420, but less than 436 here. So that's 1B plus. Actually, that's 1A minus here. I think I skipped something. Yeah, I skipped an A minus here. So that's an A minus. Anyway, you get the idea, everyone? Okay, so we count. Let me draw the lines here. So 436, these guys will have it. These guys earned an A for that section. Here's an A minus. 404, we don't see any, so no B plus. 388, here's a B. 372, that's a B minus. 356, nope. And then these guys are C's. That's a C minus. Whoops. And these guys are not so good. These are F. All right, so let me cross this out. We need to fix that, but not a big deal. So that means that for the moment, this recitation of 11 students will have 3 A's. 1 A minus B, 1 B, 1 B minus, 2 C plus C, 1 C minus, and 2 F's. Who gets those A, B, C, D's depends on the final total ranking. Notice student 4 has the highest exam total. But look on the last page. Student 4 in the final ranking is number 4, right? And what's the reason there? Because student 4's homework and quizzes weren't as good, especially quizzes weren't as good as the 3 students in front of him or her. So even though student 4 did wonderful on the exams, he or she skipped half of the recitations, didn't take the quizzes, ended up not doing so well, right? So what this is telling you is that your exams aren't everything. They determine most of what you will get, but how you end up getting also depends on your homework and quizzes. Okay, this is not right, but anyway, let's just work with those numbers and you see the idea. So now we go back to the total, the grand total. Okay? From earlier, we had 3, 1, 1, all those numbers we counted. Now, final ranking, we count the top 3, draw a line. Those students will get A's. Then the next will get the next highest grade, so on and so on and so on. Notice at this step, we also add in the bonus points. And like I said earlier, student 4 doesn't get an A. Look at student 4. Even though he or she has the highest exam scores, because there are 3 students with lower exam total but higher homework and quiz scores. So those 3 actually leapfrog ahead of that student 4. You see that? Also notice the rankings of students 5 and 6. 6 had better exam scores than 5, but 5 had better homework and quiz scores. So this is why we separate the recitation sections, and first step, we don't look at those. Because you can see now, depending on how your TA grades, these scores could be all over the place. If you have a great TA that grades very easily, then everybody might have 80s, 90s, or 100. If you have a TA that grades more harshly, you might have people with 60 and 70s. And we can't compare those two apple to apple. We have to separate them. However, on the exams, we can compare everybody on an even footing. They were all graded by the machine. Okay, so the moral of the story is that most of your grade will come from your exams, your 3 exams and your final exam. Now, the remainder of homework and quizzes, they will move you up and down, probably a third of your letter grade typically. Don't count on your homework saving you, though, because when I look at a grade book, the average homework in every recitation is in the high 80s or the low 90s. So don't count on your homework doing much. The quizzes, however, could be all over the place. So your quizzes will actually move you up and down. Up to a third of a letter grade, that's still possible. Any question? Yeah. Guys, quiet down, please. Right. Well, I can't tell you. It's different for every recitation because of the quiz scores, right? Again, if your TA grades easily, then it's 436 plus whatever. But for a different section with a different TA that grades differently, we can't use the same number to grade them. It's not fair, right? So, but we can start with the exams and then we put the quizzes back in here to think of these as adjusting you up and down by a third of a letter grade, possibly. Other questions? Okay, that's it for today. See you Wednesday.
Right. So, ever told you about my situation with meditation prices? Although, I go like the average has been going to everyone was like a 67 average, cumulative grade to almost 70 now. Yeah. But my exam was like, I got 91, 44 with a 76. I'm still wondering, I'm still within range of a. Those aren't bad, but at the same time, I'm not sure if I'm actually in range of getting a even A minus. That's why I need to actually. Yeah, it's not a range of those numbers. The closest one I think to mine is. Yeah, I'm not, but I'm not sure if I'm actually still. If I do well in the exam, if I'm actually in range of being an A minus or not. It changes every year. Yeah, it does. Yep. Until the so in the exam had like 92, 84, 92. Is it still possible to get in class? Yes. Yeah. The average is 89.4. You're better at this than me, so. Okay. Are these going to be online or on the boiler patch? Okay. Okay. Yeah. Okay. Thank you. The actual cutoffs. Okay. Okay. Yeah. Okay. Okay. All right. Thank you. Sir, let me see. Are you opening practicals? All right. See you after practice. Hi. How many points are possible on the final exam? Okay. Thank you.
Hello, I'm gonna walk back with you. How was your break? Pretty good. Was it good, like, time away just to, like, relax for a little? Turns out